Okay, we'll begin. Are there questions? Okay, if not, let me start. So let's recall what we have shown so far. So what we showed that theta, which is delta t over t, is given by minus 2/5 r. And this is, first of all, for superhorizon perturbation. And in this gauge. Okay, so this is not a gauge independent statement. Okay, but other things that you are going to do also depends on gauge, and the final result should be gauge independent. Okay. So first, let's just remind ourselves that this t, okay, which I can write as t bar. Maybe I should write this as t bar. Okay, that is the average. So t bar plus delta t. So this is measured. Yes, go ahead, please.
So this quantity is a scalar, right?
Yes.
Then I mean, and the gauge is just the general coordinate choice that we have made.
That is true.
So it should remain invariant
But
in this.
this is scalar under SO3 transformation, right?
Oh.
And as
yeah.
you have seen on the general coordinate transformation, there are two scalar parameters, right? The xi0 and then the vector xi has this gradient of a scalar. So that's why these are not gauge invariant.
Yeah, this is not a general coordinate invariant scalar.
Yeah, this is an SO3 rotational invariant scalar.
Yeah, okay.
Okay, so when you talk about these perturbations, we always classify by the SO3 transformation, right? Not by the full coordinate transformation.
Yeah.
Okay, so this is measured in the local inertial frame. Okay, but let's just remind ourselves what it was. So if we take a metric, then at xt, at a space-time point, we choose an inertial frame but inertial frame is not unique, right? Because it's unique only up to Lorentz transformation. So you have to say which inertial frame we are choosing. Okay. So we choose an inertial frame in which dx dt is 0 at that instant. Okay, this is the frame in which you are measuring the temperature. Okay. And what we had found, okay, so if you set this, right, then you can see that ds square, because the x is not changing, it's minus dt square times 1 plus 2 phi. Or I can write then the proper time, which is square root of minus ds square, will be dt times 1 plus phi. Okay, I have two first order. I'll always want first order. So square root of 1 plus 2 phi, I'm writing as 1 plus phi. So the temperature that we measured is in this time tau. Okay, this is the proper time. So the observer who is in an inertial frame with dx dt equal to 0 has proper time tau, and that's the observer who is measuring this temperature t bar plus delta t. So t bar plus delta t is measured by this observer. And our task today will be to translate this to what we measure. Okay, us sitting on the earth, what we measure, we will try to relate it to this T bar plus delta T. Are there questions? So the first thing that comes into play, and this I have already alluded to earlier, is the redshift. Okay, so let me just explain what the redshift is doing. Was there any question? So this I can also write as that if you have two successive signals separated by this proper time delta tau, okay, we are using this because the frequency will be determined in terms of 1 over delta tau, right, the intrinsic frequency. So minus 1 plus phi delta t. And proper temperature, let me write it again, is T times 1 plus theta. Okay. And we should keep in mind that we'll always work to first order in perturbation. Okay. So basically all the effects will add. Okay. So for example, if we get something like product of 1 plus phi and 1 plus theta, it's roughly 1 plus phi plus theta. Okay, but you have not got any such thing yet. Okay, I'm just giving this as a last lesson. Okay. So now we consider a photon that is traveling from some point on the last scattering surface to us. Okay. And in general, because the metric can take complicated shape, it will travel by some path. Okay. In the average background, in the FRW metric, we had seen that this was a straight line. Okay. But now because of the fluctuation, there will be a zigzagging of the path in general. Okay. So this the photon travels along null geodesic. So in particular, ds square is 0. And so this gives you minus dt square times 1 plus 2 phi is equal to lambda t square. Sorry. Let me see if I wrote the lambda t square or the previous one. Yeah, I again forgot the lambda t square here. So this is lambda t square times 1 minus 2 psi dx. So if you denote by this path by c, okay, then we have dt over lambda t is, let me write this as mod dx times, you see, I can write this as 1 minus psi minus phi, okay, because 1 minus 2 psi over 1 plus 2 phi is 1 minus 2 psi minus 2 phi, and then you're taking the square root. Okay, so this is okay to first order in perturbation theory. So I can just integrate here t ls to t naught, that's us. Okay. Now this really doesn't make too much sense unless you know precisely what psi and phi are, because in general psi and phi could be time dependent. Okay. But we'll assume for now, okay, and later on we'll discuss this a little bit. For now, that psi and phi are time independent. then one can show, then, and this I'll discuss later, one can show that C is time independent. Okay. Now this is not obvious, okay, from this, because the metric is still time dependent, right? The metric has a time dependence because of lambda and t, lambda of t. Okay. But what we'll argue later is that if psi and phi are time independent, then the actual path C that we see is time independent. Okay, and this will be important for us. Is this statement clear? Are there questions?
The path being time independent, which means what?
Means in the x coordinate system, okay, that we are looking at, forget about the time, right? In the x coordinate system, on the spatial slice in this coordinate system, this path doesn't change as a function of time. So this equation doesn't determine the path uniquely, right? Because it's an geodesic equation. In the FRW metric, we had argued that this path is just a straight line in the spatial coordinates. Now, if these are not x independent, these can be zigzag. Nevertheless, what I am saying is that as long as these are time independent, one can argue that this path in the x space remains time independent.
As in, if we translate the path to some other time, it will still be a geodesic.
Exactly. Exactly.
Okay.
Yeah, that's what it means. Now, suppose you go to a later time, right? And then see along which path in the x space it will travel from t, say TLS plus something to T naught plus something. This path will remain unchanged. That's what it means.
Okay.
And we will see how we can make use of this, right, in a minute, I mean, in the next slide. So let me write this equation again. So integral TLS to T naught dt over lambda t is integral over C d x mod times 1 minus psi minus phi. Okay, and psi and phi could in general be x dependent. Now, let's suppose that we have a signal that is emitted at TLS plus delta t. And it reaches us as T naught plus delta t. So because the null geodesic we have said is time independent, this integral remains unchanged. So now subtract. Okay, the right hand side vanishes. And what you see from here is basically that from the upper limit has changed from T0 to T0 plus delta t. So you get delta t over lambda t naught minus delta TLS. Sorry, let me write this as, this should be in general delta t naught. Okay, this is not the same as this. Okay, let me write it as TLS plus delta TLS and T naught plus delta T naught. So delta T naught over lambda T naught is equal to delta TLS over lambda TLS. So delta TLS is not the variation of the last scattering surface. Okay, that will account for later. This just says that this is that imagine that a signal starts at TLS and a little after TLS, TLS plus delta TLS. Okay, that's what this delta TLS means. And it reaches if the original signal reached at T naught, the next signal reaches as delta T naught. So this is of course one. And this tells us that delta T naught So this is the standard redshift calculation that we had done earlier, if you remember. The only new ingredient here is that as long as psi and phi are time independent, this redshift doesn't depend on psi or phi. Okay, this change.
So
Yes, go ahead, please.
lambda also contains a artifact of the perturbation, right?
No, that artifact has gone into here, right? This psi. So lambda is a background lambda. See, remember the metric? Lambda here is the average lambda, right? By definition. All the fluctuations are in
Okay.
psi and phi.
Yeah, okay.
So you have made all the fluctuations manifest, right? So other things are all background. Okay, so whenever I refer to T is the background, right? Or T bar is the background. So this tells us how to relate delta T naught to a time difference of delta T ls. But now we are going to use this here to relate this to delta tau. Okay. So dt is delta tau times 1 minus phi. You can see from here. So this I can write as delta tau times 1 minus phi over lambda ts. So this is, so that means a delta tau difference in the proper, in the local inertial frame at the time of last scattering translates to delta T naught given by this formula. That means the frequencies are related by inverse relation. Okay. And temperature is proportional to the frequency, right? Because the Planck distribution formula depends on frequency over temperature. Okay. So the temperature also are related by inverse relation. Okay. So this basically says, so this implies that delta T or T plus delta T okay, let me T plus delta T or T bar plus delta T over T bar. Right? Let's calculate the fractional change. Okay. Let me do the T bar plus delta T first. So T bar plus delta T bar that we observe is given by T that the inertial observer at last scattering surface observes. This is at the last scattering surface times lambda of TLS over 1 minus phi. So this is TLS, okay, or T bar LS. Let me write T bar LS, lambda LS, lambda TLS times 1 plus theta plus phi. Okay, because T bar plus delta T, let me remind you, T bar plus delta T at the last scattering is, we had labeled this as T bar times 1 plus theta. Okay, this is the T bar at last scattering. Okay, that's what we have done. And 1 plus theta times 1 over 1 minus phi, obviously it has 1 plus theta plus phi. Is this clear? Okay, so I'm going to write this formula again. So what we observed is that T bar plus T bar plus delta T observed is T bar ls lambda of TLS times 1 plus theta plus phi. But of course, T bar observed is a standard Redshift formula, right? T bar ls times lambda of TLS. So this tells us that delta T over T bar observed is equal to, these things cancel, 1 plus theta plus phi. And now if you remember that theta we derived as minus 2 over 5 times r, and phi we had derived as 3 over 5 times r.
There is no 1.
There is a 1. Thank you. So theta plus phi. So this is equal to 1/5 r. So what we observe today, we still have more corrections to analyze, okay, but up to this point, what we observed today is equal to 1/5 of r, right? So if you know r correlation function at the time of inflation, it's 1/5 of that will show up as the fluctuations in the microwave background temperature. Is this clear? Are there questions?
So how did you relate temperature?
How did we read the temperature?
How did we relate the temperatures at last scattering and
Yeah. So the way we related is that we looked at delta T observed is something times delta T at last scattering, right? So that means if you have a frequency, if you have a light of certain frequency, nu observed is inverse of this times nu at last scattering. So the observed frequencies are getting scaled by this factor compared to what they started with at the last scattering surface. And then we just use the Planck distribution formula, right? So the Planck distribution formula is essentially depends on this ratio. So if we now scale nu, that's equivalent to scaling T, right? If all the frequencies that are emitted from last scattering surface are observed today with this scaling, right? That means you can reinterpret this as that temperature that you observed today is the same factor times the temperature at the time of last scattering. So this is the way we had also predicted, we had also calculated, right? This is not for fluctuation, but just for cosmic microwave background, how the temperature in the early universe are related to temperature today, right? And you saw this 1 over lambda dependence that basically came, right? Lambda caused redshift, right? And that redshift we translated to a temperature variation.
Yeah, I was thinking there was some initially when we were thinking of homogeneous and isotropic universe, there was a factor of there was a volume factor just because of the expansion.
Volume factor.
And
Yes.
yeah, now there should be something like that, and if we multiply that volume factor, there would be a factor of psi coming out, right? Because in the metric we have something like dA square is minus 1 plus 2 pi d tau square dt square plus 1 minus psi dx square.
Yeah, but ultimately this temperature, the temperature that we're relating to, right, is the temperature measured in the inertial observer, right? Where these factors have already been taken into account. See, ultimately we are going to relate it to the temperature that is measured by the inertial observer, right? There it has already been taken into account. right? Because from the inertial observer viewpoint, right, this is just minus d tau square, right? And you can also scale this x appropriately.
Okay.
So because of this, I mean, since we translated everything in the distribution function that we showed, right? That was from the perspective of an inertial observer, right? If you remember the definition of energy that we gave, right, that was square root of minus G00 P0 square, right, which is the invariant energy. Right? And that is the energy that will be actually seen by the inertial observer.
Yeah.
So because of this, the volume factors work out automatically. And what is non-trivial is this non-trivial function of nu over t, right? That is exponential nu over t minus 1 inverse, right, that we saw. And that's what you can use to interpret this as a change in temperature. Okay, are there other questions? Okay. Now let me say a few words about the path of light, right? Because why is the path time independent? So let's go back to the metric. So ds square equal to minus dt square times 1 plus 2 phi plus dx square times 1 minus 2 psi, sorry, 1 plus 2 psi lambda of t square. So now let's define tau, define a new time. Okay. So I have used tau, so let me use sigma, new time coordinate sigma. Such that d sigma equal to dt over lambda of t. Okay. So then I can write the metric in this new coordinate as minus lambda of t square 1 plus 2 phi d sigma square plus lambda of t square 1 plus, sorry, this was minus. Okay, not that it matters for this argument. So this I can write as minus lambda t square 1 plus 2 phi d sigma, sorry, let me put the minus sign inside, minus d sigma square plus 1 minus 2 psi over 1 plus 2 phi dx square. Okay, for this argument, in fact, you don't even have to make this smallness of psi and phi assumption. Now, suppose that psi and phi are time independent. So t independent of psi and phi implies sigma independence of psi and phi. Okay. Now I'm going to use a property of null geodesics, okay, which you can easily prove, but I'll not try to prove it. That the null geodesic in a given metric does not change if you multiply the metric by some overall factor. Okay, even if it depends on space and time, doesn't matter. Okay, this could depend. This of course depends on time. This depends on space in general, but doesn't matter. As long as the overall there's an overall factor, the null geodesics are not affected by that factor. So which means that the null geodesics in the original metric, okay, which is here, okay, or which is here, are the same as the null geodesics in this metric. But this metric, of course, is much easier to analyze Okay, because here you see that this minus d sigma square part just separates out completely from the rest, right? Because neither psi or phi depends on sigma. So it's as if you have a product space, right? There is a time part, and then there is a part that involves the space part, okay, where the metric depends on the space coordinate. So let me write this again. So the metric in general, okay, so let's consider the metric in general of this form, minus d sigma square plus, let me take arbitrary metric, okay, gij of x di xi dxj. Okay. But the only property is that gij doesn't depend on sigma. In this case, I can easily, it's a simple exercise, okay, and I'll leave it to you to prove this. In fact, this exercise also you should try to prove that the null geodesics do not get affected by these conformal factors. Okay. But this is even simpler. Okay. So exercise, check that null geodesics of this metric span geodesics of the spatial metric GIGX. In other words, let's imagine that you are starting from a point X at some time sigma and going to a point X prime at some time sigma prime. Then if you project it down, forget about the sigma information, you just project it down in the X plane, X space, then that line is just the geodesic of the metric GIG of X. And that, of course, is what we had called this curve C. So this basically means that the path, the spatial path in the spatial slice is time independent. Is this clear? So that's what justifies this earlier assumption that we had made, that C remains the same, right? That the fact that the right hand side remains the same is based on this that fact. Okay, that the null geodesics do not depend on the spatial coordinates if psi and phi are time independent. So unfortunately, psi and phi are not, the time independence is not a good psi and phi, the time independence of psi and phi is not a good assumption. And the point is that even if you are considering super horizon perturbations at the time of last scattering, okay, what we are discussing here is the path that extends from the time of last scattering to us today. And by today, most of the perturbations that we see have already entered the horizon. Okay, and as we have seen, that once the perturbation enters the horizon, then things start becoming time dependent. So you do have to take into account the time dependence of psi and phi and correct accordingly. So in actual computation of CMB fluctuation spectrum, we have to take into account So that will just add to, so to first order, every such correction adds, right? So whatever you get extra effect due to time dependence of psi and phi, okay, we'll just add to whatever you have already found. But this has to be done, okay? And when you actually compute CMB spectrum, okay, we do take into account the time dependence of psi and phi. And this can be done because we have the equations, right? It's just that we have to analyze them more carefully, okay, which I'm not going to do in this course, okay, but this is what is done when you actually make a prediction of what the observed CMB spectrum should be for a given model. Are there questions? Okay. Now there is one final effect you have to take into account. Let me start this slide. And that is the fluctuation of the last scattering surface itself. Or I can say the fluctuation of the time of last scattering. Now, why should it fluctuate? It fluctuates because we have seen that the last scattering surface of TLS depends on various data like the photon temperature, clearly, okay, because photon temperature has to come down for enough hydrogen atoms to form. But it also depends on the density of electrons, of E minus, density of P, and so on. And each of these could fluctuate. These could fluctuate. And in principle, you should be able to figure out how they fluctuate, again, in terms of the same data, right? Because after all fluctuations are produced by the fluctuation, the primordial fluctuations, right? The RIs. So all of these you should be able to work out in terms of RI, okay? And you have to take into account, and using that, we can, in principle, compute delta TLS. Fortunately, we'll see that this doesn't actually affect the final result, okay, to first order. Again, everything is being done to first order interpolation. Is this clear? Are there questions? So for this, let's go back to one of the early slides. Yeah, this one. Okay. So T bar plus delta T bar is given by this, and now we are saying that the TLS fluctuates, right? So we have to take into account the effect of TLS fluctuation. Okay, and we'll be doing to first order, because when you are doing this, you can just ignore the effects of theta and phi in that process. So we have this relation T bar plus delta T, that is observed, is T at last scattering, lambda at TLS, and then 1 plus theta plus phi. Okay, and as I said, this will get corrected by terms proportional to phi dot and psi dot. Okay, but those I have not written down; those have to be accounted for. Okay, but this is what we have found. Okay. Anyway, those are also first order in perturbation, so this will not affect what we are going to discuss, because once we pick up delta TLS from here, all of these can be ignored, right? Because to first order, only the delta TLS here is going to of elements. So the extra effect, so extra contribution to, let's say 1 plus, we divide by t bar, okay, 1 plus delta t over t bar observed. Or maybe I can not forget about extra. So I'll also include the theta and phi. So contribution to this will be 1 plus theta plus phi plus, here there is a change in lambda. So lambda dot of TLS over lambda of TLS times delta TLS. So basically delta lambda over lambda, right? Because you are calculating logarithmic change, right? This divided by the original value. But there's another effect, because if TLS changes, then this also changes, right? Just so this of course has its own fluctuation, intrinsic fluctuations, which are here. But on top of that, if TLS is changing, then this changes simply because T bar at TLS is different from T bar at TLS plus delta TLS. So that will be given by T bar T dot over T at LS times delta TLS. Is this point clear?
We argue that TLS into lambda TLS remains constant with time.
Exactly. So that's the point, right? That if you change small TLS, right, this quantity remains constant, right? And that's what we are going to see from here. Okay, here you have written the first order variation of each of these. But then we know that lambda t times tt is constant, which basically says that lambda dot over lambda plus t dot over t is 0. Okay, so these two terms cancel. And you get back the original expression 1 plus theta plus phi, right? Which was 1 plus 1/5 r. Okay, plus the corrections due to the time dependence of theta and phi. Okay. So this, if it didn't cancel, right, this will be a complicated calculation because you have to calculate the variation of all of these, right? The photon temperature variation, of course, you have found, but you have to find out the how much the electron density fluctuates, how much the proton density fluctuates, and so on. Fortunately, all of those can be avoided if you stick to the first order formulation. Is this clear? Are there questions? Okay, if not, I'll just discuss now one last topic, and then that will be the end of the lecture part of the course. And so the last topic that I want to discuss is what is called cosmic variance. And what it represents is an intrinsic ambiguity or uncertainty in measuring CMB fluctuations. And the uncertainty basically comes from the following observation. You see, you have been talking about this quantity, right? Okay, this is what we computed from quantum theory, and this is what we are now relating to what we observed in classical theory. So this was supposed to be average over many universes. Okay? That's the correct interpretation of this. over many copies of the universe. But of course, we don't have many copies of the universe, right? We have only one universe, so we can only measure this in our universe. But we said that, okay, we'll just replace it. We'll replace it by angular average. Okay, which also can be thought of as average over different choices of coordinate frames. Okay. So if, for example, we have the last scattering surface, okay, we look at, suppose you are trying to calculate the this quantity for a particular angular separation between these, okay, which also translates to the L values, okay, but let's to visualize it's easiest to think in terms of angular separation, right? So we take 2 points at some fixed angular separation, we calculate the product. Okay. Then we take another pair of points at some fixed, the same angular separation, calculate the product, then you take another pair of points on the same angular separation and take the product and so on. And then you average. And this is, I mean, in spirit, okay, although of course it's not the same, in spirit, this is like what we do for thermal systems, right? In thermal system, what you calculate is the ensemble average. But when you actually take a system, right, and calculate its properties, we do the averaging by simply looking at different parts of the system. Okay, and that is as good as doing ensemble average. So in spirit, this is something like that, right? Instead of having an ensemble with many universes, we have only one universe. So we just do angular averaging. Okay? Do this for different parts of the universe.
So is this something like ergodicity in the sense that instead of, since we don't have enough universes, we just consider each angular bracket as a separate source of information of the universe?
Yeah, I mean, effectively that's what we are doing here. But the problem, of course, is that this has its limitation. And the limitation shows up for low L. Limitation for low L, because low L corresponds to large angular separation, right? We are basically doing averaging over large angles and then calculating the correlation function. So again, if you look at the sky for low L, you have to do averaging like this. Okay? And then you have to also do some, you are doing a Fourier transform, right? So you're doing some angular integral. Okay? And then you have some other angles at the same separation, right? So you shift it here and here. But you see that these regions now start overlapping. So these are not really independent data. These are not independent data. So for low L, okay, what you experimentally measured, right? If you try to make relate it to what a theoretical prediction could be, there is an intrinsic uncertainty that you cannot remove, okay? And because you are limited to doing experiments on one universe. Now, of course, for L equal to 2, it's not physical anyway, because L equal to 2 is the dipole, right? That, as we said, is used to fix the motion of our universe. Okay, but from quadruple onwards, it's significant. And so when you actually plot the result for the fluctuation. Right? Let me remind you what we have plotted. So you had this L into L plus 1 times CL on this side and CL on the other side. Right? You have drawn a graph like this. So this is the low L region. And so if you look at the actual data, you will find that it's always drawn with a width, okay, which is this one intrinsic ambiguity, and this is what is called the cosmic variance. And these basically you have to live with. Okay, we cannot make connection between theory and experiment to an accuracy that is better than this for the low L regions. But for high L, of course, this uncertainty goes down, right? And there, of course, the width doesn't go to zero, but it reduces enough so that you can make accurate comparison. Are there questions?
So what did you point out about the time dependence of psi and phi, the perturbations for
Yeah,
the
we cannot ignore the time dependence of psi and phi, right? Because the psi and phi that you are talking about are the involve psi and phi at late time, right? Because you are looking at the those signals coming from last scattering surface, but all the way to us, right? And psi and phi that are involved are the ones that are affecting the motion of the light along the path, right?
isn't this a like big problem in the sense that once galaxies are formed, these are order one, right? These perturbations.
Yeah, but the point is that effect, I mean, the effect of the galaxies is small because you are doing large averaging, right? You are doing averaging over large angles. Of course, along any given path, right? You have to make corrections. If, for example, you are receiving microwave background from some given direction, then you have to know what is in its path, right? I mean, if it's coming to a galaxy, right, then it's not coming from, there are lensing effects and so on. So all those have to be taken into account, right?
Yes. It's definitely not linear on anything like what we have done so far.
Yeah, so later part of the evolution is not linear, but that can be taken into account because you know the structure of the universe and you can take this into account. And again, for super horizon perturbations, right, much of this effect gets suppressed because you are doing averaging over large scales, right? So imagine that you are doing super horizon perturbation, right, and reasonably low L, okay, although not so low that you have this cosmic variance problem. Then, because you are doing averaging over large scales, right, the perturbations, right, it is true that there will be galaxies on the way, but the perturbations may still be linear because you're doing averaging, right? It's the average density that is being sensed.
Yeah.
So, as long as that remains small, and that depends on the L value, right? If you go too close, too small, right, then of course the fluctuations grow.
Yeah.
So as long as the large scale fluctuations are still small, we can use linear analysis.
Yeah.
Okay, any other question? Okay, so I think that is the end of the formal part of the course. And now the work is up to you. You have to submit the homework and then submit the project. But if you have anything to discuss in the middle, you can just send me an email. Okay, and if it's something, if you think it's something that requires a general discussion, we can schedule some meetings, or we can do it one-to-one if it's just short questions.
Sir, I had a question from field theory.
Okay, so let me then stop this, and then we can go to field theory. Anybody has any question on cosmology? Okay, so let me stop sharing and I'll just do the saving the file first.